Welcome to SanfordFlipMath. This is Algebra 2. We are working through the Springboard Algebra 2 sequence, although this content could apply to pretty much any Algebra 2 or even pre-calculus curriculum dealing with inverses. We are talking about inverses. Forgot to put that in the title, but that's what we're doing. We've done one video on inverses already, which was kind of introductory about finding inverses. This one we are going to deal with, we're going to recap finding the inverse a little bit. We're going to also talk about proving the inverse and a little bit of graphing both the original function and the inverse function. That's a lot to do in one video. We're still going to try and keep it short. Keep in mind that this video is really a review video. We're not spending a lot of time laying out where all this comes from. We're just kind of recapping and doing some problems. So this is the quick version. Okay. So first of all, in finding the inverse, the basic idea of inverse is it's about switching x and y is really the heart of finding the inverse. That's the big chunk of what inverse is about switching x and y and solving for y, and then a lot of times there's some notation involved in there. So if your function's written like f of x, g of x, that kind of thing, then usually we just rewrite it in terms of a y equals to make it easier. And then we do the switching, solve for y, and then if it started out as a f of x, then at the end we should write it as f inverse of x, typically how that's stated. A very speedy example might be something like y equals 3x minus 7. And if we were going to do inverse, then what we would do is actually take this x variable and the y variable, and we would swap them. So that's going to be over here, and then the rest of this is still 3 something minus 7. Okay, so it did say y equals 3x minus 7. Now it says x equals 3y minus 7. And do a little switcheroony, and then after that it's just solve for y. So we're trying to get y by itself, so we're going to add 7 to both sides, divide by 3, and there are lots of ways to leave this. Whoop, you're not supposed to see that, that's for the next slide. Y equals x plus 7 over 3. You could leave it like this. Many people don't like that, they don't feel like they're done. So you can divide each term by 3, and there it is. Now, the only other catch is if this would have started out, let's say this was g of x, then at the end we'd be writing g inverse of x equals whichever one of these you like. Okay? All right, that is it for how to find an inverse. At some point you'll deal with more complicated equations where it might take some more effort to get y by itself, but this is where we're at right now. Okay? With that in mind, let's talk about proving it's the inverse. Because switching x and y and solving for y doesn't prove it's the inverse. All it does is find you the inverse, assuming that an inverse actually exists, because there are situations where the inverse is not a function, etc. Ooh, where'd that go? That went fast. I just flung it and it went. Okay, so this is basically what happens to prove something is the inverse. This is what the definition of inverse includes. It basically says if I put these functions inside of each other, and sometimes they're f of x and g of x, and sometimes they're g of x and f of x. Isn't that clever? Okay, so if somebody's saying f and g are inverses of each other, then the way to prove it is to do composition. Put one inside the other, and if the answer after you're done simplifying is x, then you just have to do the same thing on the other way around, put the other inside of the one. And again, if you get x, if both of these happen, then ding, 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 yep, it's inverse. Okay, so if we have something that says, prove it's the inverse, I know you saw that. If it says something like prove the inverse, then you have to do f of g of x. If it said, use the definition of inverse to find out if these two are in fact inverses. Well, that's the same thing. Okay, so this is the definition of inverse, or proving that it's the inverse. Okay, all right, and last but not least in our little list here is graphing the original and the inverse on the same graph. Well, if you do that, then the original graph and the inverse graph will be reflection images across the line y equals x. Okay, so what we're talking about here, okay, we don't need that anymore, so we can get rid of it. And we don't need that anymore because those were the other pages. Okay, so what we're talking about here, here's a quick little version. Okay, let's say I have y equals 1/2 x plus 3. So something like this. Okay, let's say I spend a lot of time finding the inverse, and let's say it's something clever like 2 times x minus 3, which most of you will be happier with as y equals 2x minus 6. Okay, now this is not going to look cute because I'm not working on a grid, so this is going to be really rough. Oh, I missed. Oh, let's just pretend. If I draw the line y equals x through here, if I draw that line, hopefully you can see, and again, this is a very quick and very not so careful example, that if I take this black graph and flip it across the dotted blue line, if I take this black graph and flip it across the dotted blue line, it becomes the red graph. Okay. If you reflect the original function across the line y equals x, that's the line that's y equals 1x plus 0, slope of 1 with a y-intercept of 0, then you get the inverse graph. Okay. You can also work with ordered pairs. Okay, remember when you do inverse, ordered pairs switch, they trade. So if you're working on a graph and you want to make the graph of the inverse, you can trade ordered pairs on individual points. Like for instance, if I look at on this first equation, the point 2, 4, then the graph on the inverse would have the point 4, 2. Okay, so these guys can just trade. They can switch back and forth. Okay, and so that's kind of that issue. One other thing I want to point out again is notice what happens with the slopes. The slope of the original was 1/2, and the slope of the inverse was 2/1. And again, remember, slope is y minus y1 or y minus y2 minus y1 over x2 minus x1. There it is. So it's change in x over change in y over change in x. Sorry, I'm trying to go too fast. Okay, rise over run. But on the inverse, remember that x and y switch. So what used to be the x is now the y. What used to be the y is now x. So the change in y over change in x swap because the x and y is swapped. Okay. All right. Having said all that, that was just the speedy recap. We just did like 3 or 4 days worth of work in 8 minutes and 20 seconds. Okay. We're going to do one example of a little bit of everything. And here's a recap of what we just said. Okay. And we're not going to spend a lot of time on this. This is going to be our only other example. Okay. All right. So first off, find the inverse. Now I'm giving you one big Oakley equation. We're going to do all three. My advice to you is hit pause right now. Everything that comes after this is stuff that you should already know how to do. I understand that this is to help fill in the blanks, but you should be able to do all of this. Okay, so you have 3 separate problems here. Find the inverse, prove it's the inverse, and graph both on the same graph. And you should see that whole reflection thing happen. Okay, so I'm going to do it, hit pause, and then come back at the end and check to see that yours is all awesome. Okay, so here's how it looks. We're going to find the inverse. So again, we're going to rewrite the function with y instead of f of x. Okay, that's already done. Okay, so we're going to switch x and y. So what used to be y is going to now be in the x position. Okay, and you're hearing the markers click around, and what used to be x. All right, so I switched them. So x and y traded places. Okay, we're going to do a little bit of solving now. So I am not a big fan of fractions, so I'm going to get the fractions out of here. Okay, so 2x equals, now 2/1, these 2's divide out. So this becomes y plus 1 and then if I'm solving for y, I can subtract 1 from both sides. Remember, these are not like terms, so I'm going to say now, well, I know that's going to bug somebody, so I'll write it first, and then I'll switch it around. So 2x minus 1 equals y. So the inverse is y equals 2x minus 1. Okay, so we have just done find the inverse. Okay, so let me recap again what these equations are. Y equals x plus 1 over 2. Y equals 2x minus 1. Now, please understand, I know some of you are already thinking, you know what, I see that pattern. Okay, I need to see the steps because the patterns don't always help you for every little thing. Okay, so this is the original. This is the inverse. Okay. All right, so now what we're going to do is prove that these two are inverses. So now they should be because I just solved them, so I'm hoping they are. But what I want to do is prove it using the definition of inverses. And the definition of inverse says, if I put one inside the other, I should get x, both ways. Okay, so what I'm going to do is I'm going to take this guy right here, the red one, and I'm going to rewrite it. I'm going to say something plus 1 over 2. So this is like f of x. And what I'm going to do is put f inverse, what I think of as a f inverse, in here. Okay, so let me put some notation. Really what I'm doing here is f of f inverse of x. Okay, now I'm going to do some simplifying. So a negative 1 plus 1. So this is now 2x over 2. 2x, well, 2's divide out, so I'm left with x. Awesome. Okay, I'm going to do the same exact thing, only different. Okay, so I'm going to take the blue one now and say 2 times something minus 1. Well, what's the something? The red one. Okay, so I'm putting one inside of the other, replacing x. Don't write times x, I'm replacing x. Okay, so 2 over 1 and the over 2's divide out, leaving x plus 1 minus 1, which is x. Okay, so I did f of f inverse, like f of g, and I got x. I did f inverse of f, g of f, and I got x. I have just proven they are inverses. Okay, so the proof for this is not a geometric proof. It's not statements and reasons. It's just that. Okay, and one last thing we're going to do with this is we're going to graph both the original and the inverse, and I want you to see the reflection thing. Okay, all right, so here we go. Okay, so here's my original. Now, again, I know most of you don't like that form, so I'm going to rewrite this. Y equals 1/2 x plus 1/2. Now, the whole idea here is this is just a little bit of algebra. This is the same thing as x over 2, which is the same thing as 1/2 times x. Half of x is the same thing as x being divided by 2. And then I did plus 1/2, okay, because it's just the 1 over the 2. Okay, so let's do some graphing. So at y-intercept of 1/2, I'm now going to go up 1 and over 2. And I can draw a little line through there. Something like that. Okay, I'm going to fix that a little bit. Okay, and let's make that red. And for you purists out there, we'll even put some arrows on. Okay, so there we go. Okay, next one, a little bit easier. Okay, slope, y-intercept's -1. Slope is 2, so I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. Okay, and again, we'll do this. Same exact process. Sorry, I just want my lines to actually look kind of straight. I mean, they actually look pretty good. Okay, this is blue, and again, we'll throw some arrowy things on the end. Okay, all right, so now I guess my question is, does it look like these are, what's supposed to happen is these are reflections across that line y equals x. Okay, well, let's see if that actually kind of bears out. So I'm going to draw a line on the line y equals x. Well, y equals x is supposed to have a y-intercept of 0, 0 and a slope of 1. Okay, so here we go. Something like this. Okay, and I need you to kind of eyeball it then and say, does it look like if I reflect the red line across this black line, okay, which I'm going to make dotted because it's not really there. All right, and again, for the arrow people, it doesn't really matter. Does it look like this blue line would reflect across here and become the red line? Does it look like this blue line would reflect across here and become the red line? You can even spot some little ordered pairs. Like for instance, this guy right here, that point looks to be 5, 3. Well, if I go to the point 3, 5, it's on the line, and these are images of each other because of the whole idea of switching x and y. Okay, all right, so 3 big ideas with inverse. Switch x and y. Okay, that's here. Okay, switch x and y, solve for y. If you want to prove inverses, then you have to put one function inside of the other, and they should end up being equal to x after you do that. Okay, and then the last one, the original and the inverse are supposed to be reflections of each other across the line y equals x. That's very specific. All right, the video went a little bit longer, but I did more than I expected to. So, you know, this is an extra video. This is not something you know, that we already talked about all this in class. So, all right, well, if you have other questions, you know where to find me. And thanks so much for coming. Thanks for hanging out with me wherever you are. And I guess we're out of here. SanfordFlipMath. Bye.